So a few days ago, I was reading a story about the Psyche mission. The NASA spacecraft is going to be taking photos of the incredible Psyche asteroid in a few years from now. And turns out this mission already had some incredible success in something that was never tried before until relatively recently: communication through lasers. Also known as deep space optical communication, that literally is a laser that's being fired from the spacecraft and then received back on Earth in order to transmit data a little bit more effectively. And then I remembered why this was important. Project Starshot, which is one of the reasons this is being tested, to see if it's possible to communicate with objects really far away using laser technology. And in case you either forgot or never knew about this unusual project, here's a super brief reminder. This was announced back in 2016 and involved a lot of high-profile people, including the Zuck of Facebook. That's basically where a lot of money is supposed to come from. And here the idea was to use lasers, very powerful lasers, to shoot at a tiny solar sail that would then be accelerated to 20% of the speed of light by using solar sail technology in order to then travel to the nearest star to us, Proxima Centauri, do a kind of a flyby, take a few snapshots of what's going on here, transmit them back to planet Earth, and hopefully repeat this sometimes in the future. In essence, achieving the first ever exoplanetary photos by direct flyby from planet Earth. And obviously back then, everyone got super excited, with everyone's question being, so when pictures? Or more importantly, is this even going to happen? Or is this just another one of those grandiose schemes like the, LK-99 superconductor that never happened? Or that promise of the nuclear fusion that's going to be saving humanity from itself sometimes in the next 20 years? Which is something that's been promised every 20 years for the past, 70 years, I think. And so I got super curious to see where this project currently is. Has it been officially abandoned? Did the researchers realize it was unachievable and just forgot to tell us about it? Or has it been silently going on in the background, hoping to actually achieve this sometimes in the future? And yeah, turns out the answer is that latter one. It seems to be still going on, and surprisingly, and for some reason nobody told me, extremely recently in my home city of Montreal, there was actually an interstellar research group symposium that hosted this wonderful person, Professor Harry Atwater, that literally discussed this project in detail, where it currently is, and provided a huge amount of interesting information, including a lot of current achievements and where the project stands, where it's headed, how long it's going to take us to, get to Proxima Centauri, and kind of answers the question of when pictures. So yeah, this is still going on, it has not been cancelled, it's going to be going on for a very long time, they're pretty serious about it, and holy cow, they've actually done quite a lot of research about this. A lot of the achievements out of this project so far are absolutely incredible. Also, it's not going to look like this at all, turns out. All of this was just animation and shown us what it might look like, but apparently none of these shapes are going to work, and all of this is going to look entirely different if it ever happens. And so, hello wonderful person, this is Anton. Let's discuss this project in more detail, talk about what's been achieved and what can possibly happen if it does occur, but in the end I'm also going to be a little bit more pragmatic and talk about the reasons why I still think this is not going to physically happen, for a lot of reasons, including a potential international disaster. And so, Breakthrough Starshot. What exactly did the researchers learn in the last 7 years? Okay, so first of all, this is all still extremely theoretical. After watching this video, I think a lot of us assume that this is something that's going to be built maybe in 5 to 10 years from that particular point. Yeah, that's not even close. The unofficial launch date for this is right now 2050. So yeah, most of you are very likely going to be dead. Sorry. However, if we're not dead, and we're still around to see things and to possibly appreciate things, somewhere on the planet there's going to be something that kind of looks like this. An enormous array of really powerful lasers, in this case approximately 200 gigawatts in power in total, able to essentially fire the lasers all at the same time, at the same phase, and then propel something at extremely fast velocity by using the same principle as a typical solar sail. And here the main researcher even did a bit of an example and crunched the numbers, showing us how powerful all of this would be. Here he sort of compares this to a typical laser pointer and says this is kind of like pointing a laser pointer at a tiny object a few grams in mass, for example some kind of a thumbtack. If you were to shine a laser pointer at this thumbtack for approximately 1 week, in outer space it would achieve a velocity of approximately 1 millimeter per second. Definitely not a lot, but it is going to start moving in a certain direction. But if you take a bunch of these laser pointers and put all of them in a desert somewhere, and then have all of them shine at the same time with a total power of 200 gigawatt, yeah, that thumbtack is going to fly really fast and can physically achieve a fraction of the speed of light in around anywhere from 10 to possibly 20 hours. The current goal is to achieve approximately 5g of acceleration for the first few hours, which will slowly decrease to maybe 1g by the time the lasers stop firing. And so at that point, the object is going to be moving super fast. And so the actual theory is sound. Physically though, things get a little bit more difficult. First of all, where do you get so many lasers and how do you build this? Second of all, you have to find a material that's able to withstand all of this and basically not get completely melted. Third of all, you have to work out the logistics, the shapes, and everything else in between, and somehow make a large enough spacecraft out of this, and not just some kind of a tiny thumbtack, so it starts to physically fly into a direction of Proxima Centauri. And holy cow, did they do a lot of research in the last few years. For example, there's been a lot of research on the Lightsail material, just to figure out what's going to work, what's not going to fall apart, not overheat, and so on. Currently, there are two possible candidates that already exist and could physically work for sure. Silicate nitrates seem to be possibly the best, extremely high strength and very low absorption, suggesting that they're not going to fall apart and not going to melt, or possibly molybdenum sulfates or disulfates, which don't really cost as much, can be produced en masse relatively quickly, and have very good optical properties as well. But much more importantly, they physically developed really intriguing computer simulations to test all of this, including the possible shape. And it turns out that the shape itself was somewhat challenging. So yes, something like this is unlikely to work. It's not going to fly straight and might start wobbling around or even fold completely. And so here they actually ran a bunch of simulations showing how all of this sort of reflects if you start firing powerful lasers at various types of shapes. Turns out parabolic shapes seem to be the most stable, and specifically if they're spinning around. At some point you can actually achieve a shape that doesn't really change much, does not fall apart, does not overheat, and stays relatively stable. Alternatively, they can also start using the more advanced metamaterials that are known to have very specific properties inside that can sort of act in a very similar way and produce, I guess, internal parabolas. And here, as you can see, it does kind of stay stable relatively long. This is all from recent research from just a couple of years ago, and something that has been already created in a lab just to test this, with actual microshapes and physical lasers. So by itself, this is already quite some progress. They've basically worked out how to maybe potentially accelerate something using laser technology without the use of any propellant. But what about the spacecraft itself? Well, it's currently designed to look something like this. Yeah, this is like an alien probe right there. Roughly around 4 meters across, and basically being a kind of a pancake where everything, including cameras, including energy production, and even communication, is designed to be super flat and sort of pancake shaped. For example, number 1 represents the sail itself, that's the engine of this whole probe. Number 6, or these tiny circles, represent various cameras on board, with some specifically designed to take pictures without any lens. Number 2 is the communications array, designed to send out a relatively weak signal back to planet Earth in order to then intercept it from Earth. 3 and 8 are the computers and processing, which by then should be really advanced. And the other numbers are various types of sensors. So by itself, this design is sort of brilliant. There's basically so much here that's condensed into an extremely thin object with a total weight of just 14 grams. And the sails here only weigh 4 grams. That's ridiculous. That's literally a thumbtack, just squeezed and stretched to a very large shape. But there's obviously a problem here. The problem is that quite a lot of this technology is still a little bit science fiction, as in very theoretical, does not exist yet, and is still only being actively developed for potential future use. But at least one type of technology here is super exciting, and the research that a lot of this is sort of creating can actually end up creating something absolutely incredible. And I'll explain what this is in a few seconds, but first there's maybe a few concerns that I currently have that I'm not entirely sure how they're going to resolve yet. This was not discussed yet, and I don't think there's a solution yet either. First of all, the energy production. Here it's supposed to involve some kind of a micro-RTG or radioisotope thermoelectric generator, which in previous missions kind of looked like this. This is a typical one we usually find on various interplanetary probes, and is supposed to work for at least 30 years, as well as produce approximately 1 watt of power, at least at its peak. To be honest, I'm not entirely sure how this is going to be achieved. It sounds kind of incredible if they can achieve this. For example, a typical RTG today can maybe produce a few 100 watt of power, but it's going to weigh a few 100 kilograms. Taking that and making it into just like 1 gram or so, to me currently that sounds a little bit impossible. But not a nuclear scientist, and so they might find a way. Since this was not discussed, I don't think they solved this issue yet, but that's their proposition for now. The second issue that's also kind of related to this is communication. So here at the peak is going to produce approximately 1 watt of power to run everything. And that's of course going to include radio signals. And so if you send a 1 watt radio signal from Proxima Centauri to planet Earth, by the time the signal gets to planet Earth, its maximum power is going to be something like 1 times 10 to the power of maybe minus 30 watt, so essentially an extremely weak signal. And we know all of this based on signals received from, for example, New Horizons or the Voyager probes. By the time these signals are received on planet Earth, they're roughly around 4 times 10 to the power of minus 19 watts. And that we can still hear using some of the most powerful radio antennae on the planet. But from Proxima Centauri, the strength of the signal is going to be, at best, at least 1 trillion times weaker. It's going to be almost impossible to tell it apart from the background noise, and thus potentially make this mission sort of useless, at least based on current technology. But the receivers are discussed in this particular talk, with some suggested to look something like this. But the thing is, we wouldn't just need one of these, we would probably need thousands, if not millions, across the entire planet in order to receive these extremely weak signals from basically 4 light years away from planet Earth, making this already an extremely challenging mission in terms of logistics. So imagine having like 1 million of these across the planet, and imagine how much money is going to be spent just building the receivers. But theoretically, it seems to be possible based on the research from this particular talk. And more excitingly, if we could somehow build quite a few of these receivers on the planet, it can actually be used for listening to a lot of other stuff that's not even related to the mission. I mean, this would actually propel SETI research to a new level. By being able to hear these much weaker signals, it would open up an entirely new era of radio astronomy. Even if we just had like 100 of these receivers somewhere, it would allow us to hear and triangulate extremely weak radio signals coming from any direction in the universe. That's absolutely incredible. So yeah, I wouldn't really discount this research just yet. It might actually lead us to something super exciting. And speaking of exciting things that seems to be kind of connected to this, a lot of the technology here and a lot of these propositions directly depend on this: lensless color cameras or steerable communication antenna. For the lack of, I guess, better explanation, these are metamaterials physically designed to receive and send signals without any moving parts in any direction or without any lenses to amplify anything. And all of this is connected to research from just the last couple of years on a lot of different metasurfaces. Specifically the field known as optical phased arrays and active metasurfaces that can basically both act as a receiver and, I guess, as a sender, three-dimensional structures inside the material that can also be made extremely thin. With the first technology that's going to be coming out of this really soon being physically cameras that don't need any lenses at all, but that can see the world in a lot of different ways that normal cameras cannot. So yeah, here we're talking about some kind of a super futuristic cameras that will very likely exist in the next decade. But the first analysis of some of these receivers has been conducted to some extent as well. Here they actually show us how we might be able to create some of this and how it technically could work, but just not yet in the near future. On top of this, you have to somehow track where all of this is going and basically make sure that the spacecraft is flying into the correct direction toward Alpha Centauri. To achieve this, they propose something relatively simple, an orbiting beacon with the orbit you see right here. This would then be used to track the spacecraft and also track the motion of the spacecraft, but then to also guide the lasers in order to make sure they fire in the direction where they have to fire. So basically here, a satellite in space is going to be used as a guiding star. Based on the calculations, it looks like it's going to be able to maintain the tracking and ensure accurate firing of these lasers up to about 20 hours, which is precisely what they would need in order to propel this craft to these very high velocities. And honestly, just based on these propositions, this is some really advanced stuff. It might physically revolutionize optical communication in space, and obviously lead to these really cool technologies like lensless cameras and antenna-less receivers. So all of this metasurfaces stuff and all of the propositions coming out of this are definitely not far-fetched, not crazy, and could be physically used in a lot of future technologies. And a lot of previous concerns and a lot of previous issues that I actually had about the project seems to have already been resolved. For example, heating. All of these simulations showed us that the maximum heat is going to be about 600 Kelvin, meaning that the materials are not going to melt, with the physical spacecraft being able to withstand all of this and not be folded, destroyed, or melted. But then we have a lot of buts. Basically, a lot of problems that are still not resolved and might not be resolved because things here just get really expensive and really dangerous pretty quick. Let's start with the obvious. This is the photon engine or the lasers that are meant to propel all of this. By today's standards, anything like this would be impossible to make, just way too expensive. To produce 200 gigawatts, first of all it would take 10 years to build, and you would need about 700 million lasers, all connected together, all working at the same time, and all being able to produce energy that's just currently unachievable. Which is why here we're kind of presented with the more realistic graph. Assuming that the laser cost decreases as it does right now, and assuming that we do get lasers that are able to produce even more power, by 2050 it might be possible. But at modern day costs, it's just way too expensive. Actually, even at these costs, the current estimate is about $300 to $400 billion. $500 billion just for the lasers. So yeah, this would not be a cheap project, and I'm sure even Mark Zuckerberg didn't really know what he's signing up to, because I don't think Facebook even has that much money. I mean, Meta. Anyway, on a more serious note, at least once these lasers are operational, the physical cost is not going to be as much. A single launch here, based on the energy costs, would only be about $150,000. In terms of what's being achieved here, that is actually pretty cheap. But we're only launching a spacecraft that's about 14 grams in mass, and it's unlikely to work for anything much bigger than that. But based on this talk and based on everything that was proposed, it looks like the proposition right now is 2050s. By then, the technology will most likely catch up, the overall cost will have come down, making the overall project potentially viable. Something that I'm sure most of us had no idea about when this video was shown. We thought this was going to be like maybe 2025, maybe 2030, not 2050. Yeah, that's way too far. And in terms of physical costs, this would be the most expensive mission ever. For example, the most expensive mission now, the International Space Station, was only $150 billion. That's like at least double, possibly way more. And so despite all of these really cool achievements so far, let's also talk about the more pragmatic stuff. Let's talk about the reasons why I still think it's most likely not going to work and very likely will never happen. Yeah, sorry about that. And let's ignore the cost for now completely, or the fact that you have to build an enormous laser somewhere, have thousands if not millions of receivers around the planet, have to have a lot of coordination, a lot of agreements from a lot of different governments. Let's start with, I guess, the basics of physics and the basics of, human society. First of all, the probes. Now this has to travel for about 20 years at very, very high velocities through a not so empty space. There's a very, very high chance that at least at some point, this probe that's about 4 meters across is going to bump into something. Doesn't have to be a big something, even a few atoms across, but it's going to definitely cross something. And when that happens, at 20% the speed of light, even if it's a tiny, tiny object, it's very likely going to completely shred the spacecraft. And we'll never get any pictures or any data out of this or even of this event because it's going to be so sudden and so explosive. At these super high velocities, the kinetic energy of hitting anything is absolutely enormous, and the chances of crossing some kind of a space dust particle at some point are definitely not zero. And so that part is definitely a bit of a challenge and cannot be resolved in any way. But then there is this, the laser firing. Okay, you're firing a laser into an object in outer space through the atmosphere of the planet in someone's neighborhood. First of all, I don't think a lot of people are going to appreciate this. Second of all, this might have some unexpected effects on the atmosphere because we're talking about really powerful lasers. Third of all, we're going to have quite a few upset people who really like birds and that are going to see that a lot of birds got cooked by this. Because remember, this laser is going to be fired for possibly 10 to 20 hours in total. And third of all, I'm sure there are a lot of different reasons for why you wouldn't want to fire a super powerful laser into the atmosphere just to accelerate a spacecraft. And the biggest reason why this might never happen is actually geopolitical and nothing else. Having such a ridiculously powerful laser that's able to focus and track anything in the night skies with extreme precision, that sounds really familiar. It was known as the Strategic Defense Initiative, Star Wars Initiative, proposed by Reagan back in 1983, with the main point being lasers that can shoot down any incoming nuclear weapon. And this here is that times 1,000,000. Any country with this technology would be immune to nuclear attacks and would completely reshuffle the balance on the planet, making a lot of other countries super upset, possibly leading to a major conflict. On top of this laser can also be used in, obviously, offense. By having a mirror in space, you can then redirect this anywhere on the planet, killing anything anywhere. Yeah, that's not going to look pretty, and that's pretty much where this technology is headed. Just like with every major technology in the last 100 years, you always have to ask yourself a question, yeah, but can we kill with that? Can it be used as a weapon? And in this case, it's a really big yes. And that big yes is a big no-no. Mostly because of the potential implications and potential dangers all of this can lead to. So for me personally, or based on what I know about the geopolitical issues, I don't think it's going to be viable anyway. You cannot possibly produce this without making someone out there extremely upset. Upset to the point where they're going to start a war. And so yeah, it's not going to very likely happen, but we should not stop the research, for one reason. The actual technologies that are being developed and the stuff that's coming out of this is really cool. For example, having super efficient solar sails is already really exciting. Or a way to communicate using lasers and transmit data using nothing but a tiny surface. All of this is super cool. Also, the design of the spacecraft and everything that's been achieved so far is also really awesome. But the end goal, the actual Breakthrough Starshot, now that I don't think is gonna happen. And hopefully I made it clear why. Anyway, I'm sure there's going to be more about this, and I'm sure we'll have more updates in the next few years. But until then, check out all of the links in the description, including that symposium that I mentioned. And thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.